So you can start now.
Welcome to webinar series of Ministry of Earth Sciences. I am Dr. Mrutyunjay Mohapatra, Director General of India Meteorological Department. Today it is the 12th talk in this webinar series of Ministry of Earth Sciences. I will be talking about the cyclones, its basics, dynamics, and the predictions. I hope this webinar series is very useful to our academicians, students, research bodies, and overall the general public. In this series, as we know, India is very prone to tropical cyclones. We have kept a talk on basic features of the tropical cyclones with special emphasis over the North Indian Ocean. This talk will be about of 1 hour duration. During this period, you can send your questions. At the end of the talk, I'll be answering to your questions. Thank you. We will now proceed towards the presentation on cyclone, basics, dynamics, and the prediction. If you look at the recent cyclones like Amphan, you will find that the cyclone causes a multi-hazard scenario because of the various types of severe weather associated with the cyclone when it crosses the coast. It causes heavy rainfall leading to flooding in inland areas. It causes contamination of water supply systems, sometimes land subsidence, landslides. It also causes the destruction of crops, vegetation, and livestock. The cyclone is associated with very strong winds, and these winds causes the damage to structures, loss of power and communications, injuries, loss of lives, and also damage to the standing crops, vegetations, livestock. The storm surge, which is called as the killer of the cyclone, causes the flooding of the coastal areas and erosion of the beaches, loss of soil fertility from saline intrusions, damage to structures, and also because of the soil erosions, there can be collapse of houses, and also power and communication system can also be affected. If you look at the diagram on the left bottom corner, that is the picture of a tropical cyclone. And next to that, the bottom, you will find that how a tower has been collapsed because of the tropical cyclones. Similarly, at the top left corner, you will find that how the ships and large boats are pushed towards inland because of the tidal waves and the winds. In the middle, you will find that one person is reconstructing his house. This picture I have taken while I visited in 2008 Myanmar after this notorious cyclone Nargis, which devastated Yangon Delta. This is a person who has lost all their kith and kin. Nobody is there in his family. He is alone. He has lost everything, but still he is constructing his house because he wants to live. So considering these two aspects, that cyclone has a devastating impact in terms of loss of lives and property. At the same time, every human being wants to live. So as an early warning service provider, as a disaster manager, it is our prime duty to ensure the services so that it can minimize loss of lives and properties. It can ensure the living of each and every person in this world in the face of devastating tropical cyclones. So these pictures inspire us time to time while dealing with the early warning of the tropical cyclones. Some of the facts about tropical cyclones I just want to put off in your presence. If you look at the statistics, about 33% of hydrometeorological disasters in the world during the period 1970 to 2019 has been due to the tropical cyclones. So you can just imagine what is the contribution, devastating contribution of tropical cyclones. 1 out of 3 events that killed most people globally is the tropical cyclone. TC means tropical cyclone. 7 out of 10 disasters that caused biggest economic losses in the world during this period are the tropical cyclones. It is the key interest of 85 World Meteorological Organization member countries which are prone to tropical cyclones. Casualty of 300,000 in Bangladesh in 1970 is still ranked as the biggest casualties for the last 5 decades due to the tropical cyclones. So what I want to highlight here that though tropical cyclone is notorious worldwide, in the Bay of Bengal region especially, it has become the most notorious, and we have got the notorious record of highest deaths due to tropical cyclones. Considering all this devastating potential of tropical cyclones worldwide, the scientists, engineers, disaster managers, they have always tried to imbibe or to apply the modern technologies for operational services to mitigate the disasters due to tropical cyclones. Now, considering India, we have done a study about the disaster proneness of the tropical cyclones, or the hazard proneness. Now, this study was taken up based on the frequency of cyclones crossing a district and the intensity of cyclone crossing the districts, the wind associated with the cyclones over the district, and probable maximum precipitation due to the tropical cyclones over the district, and the probable maximum storm surge or tidal wave which can cause over the districts. Now, considering all this, you will find that we have divided all the coastal districts into 4 categories. One is the very highly prone categories, that is red colors. These are the North Odisha and West Bengal coastal districts, followed by some districts in Andhra Pradesh. And then blue color is the highly prone districts. These are mostly in the east coast, and in the west coast it is Maharashtra and Gujarat. And then comes the moderately prone and low prone districts. What you find actually the entire west coast and east coast and Andaman Nicobar Islands, Lakshadweep, are prone for the cyclone hazards. But however, the degree of hazardness is higher in the east coast, especially over North Odisha, West Bengal, and parts of Andhra Pradesh. Now, in the face of this devastating nature of the tropical cyclones, India Meteorological Department has taken various measures in recent years. And you will be happy to know that the cyclone forecast accuracy of India Meteorological Department is quite good. It has improved in recent years. And if you compare the leading centers, we are second to none. Our cyclone track forecast accuracy has reduced to about 86 kilometers in the recent years compared to 125 kilometers before 5 years. Similarly, if you look at the uncertainty in a track forecast, that is cone, whatever we show in the track, it is reduced by 30%. And the 24-hour landfall forecast error, that means if I say the cyclone will cross near the point X, earlier we had error of about 91 kilometers. That means it may go up to X plus 91 or X minus 91. But in recent time, it is 42 kilometers. That means if I say cyclone is going to cross near Paradip, it will be 42 kilometers to the north of Paradip or 42 kilometers south of Paradip. So this type of minimum error enables disaster managers to take the focused action over a number of districts which are most prone or likely to be prone due to the landfalling cyclones. Similarly, the error in intensity forecast or wind forecast has also been less. It is about 10 to 15 knots, or you can say about 20 to 30 kilometers per hour. So similarly, there has been the improvement in accuracy of other significant weather events. So as a result, if we just look at the outcome of this improved forecast is that there has been no cyclone in recent years since 2013, you can say, where because of a landfalling cyclone, the number of deaths has increased more than 100. Always it has been less than 100. But if you compare it with the previous cyclones, Odisha super cyclone, for example, it was 10,000. So we have been able to reduce the number of deaths from 10,099 to about less than 100. Say, for example, 25 in case of Bulbul, and 64 in case of Fani in 2019. So this is the achievement during 20 years. And this has been possible because of the combined effort of all the agencies at the state and central level, apart from early warning service providers as India Meteorology Department and Ministry of Earth Sciences. So you may ask, how did it happen actually? What was the game changer? Is it Odisha super cyclone which caused death of 10,000 human losses? Yes. After the death of 10,000 people because of Odisha super cyclone, there was hue and cry worldwide and also in our country. There was demand, there was opinion from the media and general public that it was a scientific failure. Thereafter, a number of initiatives were taken at state and central level, including Minister of Earth Sciences and National Disaster Management Authority. National Cyclone Risk Mitigation Project was taken off in 2005, and Modernization Program of IMD was taken off in 2007. Under this Modernization Program of India Meteorological Department, cyclone warning system was improved, and results started coming out because of the improved system from 2009 onwards. During this modernization program of cyclone warning system and modernization program of IMD, all aspects of cyclone warning systems, including monitoring, analysis, forecasting, modeling, warning products generation, and dissemination, were addressed in an integrated manner. Now, with this background, if you just look at what a cyclone is. A cyclone is a low pressure system. It develops from a low pressure area where wind rotates anti-clockwise in northern hemisphere and clockwise in southern hemisphere with a minimum sustained wind speed of 34 knots or 62 kilometers per hour. World Meteorological Organization has defined it as a tropical cyclone, which has got different names like hurricanes and typhoons. It is a synoptic scale system. That means it has a size of about 100 kilometers to 1,000 kilometers. It is a non-frontal system. That means there is no gradient of temperature in the area where the cyclone occurs or cyclone develops. The frontal systems like warm front, cold fronts, they develop over the mid-latitude, affecting Europe and USA, etc. And these tropical cyclones develop over the subtropical waters. The tropical cyclone is an organized convection. You will find that the convective clouds in a tropical cyclones are organized. It takes a shape. Sometimes you can find out the eye of the cyclone. It is a complete a structure. Sometimes people compare the shape of the cyclone with the emblem of the Darshan. Sometimes people compare it with the Milky Way, our galaxy. And sometimes the people compare it with the child in the mother's womb or Kamasef. So, however, qualitatively, it is a synoptic scale system with a size of 100 to 1,000 kilometers. It is a tropical system. It is a non-frontal system. It develops over the tropical waters, and it has got a definite cyclonic surface wind and organized convection. Quantitatively, it is defined as a low pressure system where wind rotates anti-clockwise with a speed of about 34 knots or 62 kilometers per hour in northern hemisphere. In southern hemisphere, it rotates clockwise. These tropical cyclones have got different names. Mechanism is same, but it is having the different names. For Western Pacific, these are called as typhoons. In Australia, it is called as Willy Willy. In Mexico, they call it Goranjo. Philippines, Bagias. Indian seas, we call it cyclones. Atlantic and Eastern Pacific, they call it as hurricanes. Now, if you just look at the structure of the tropical cyclones, you will find that it has got a horizontal size of about 100 to 1,000 kilometers. Vertically, it can extend up to 10 to 15 kilometers. So it is such a giant system. It has got a wind speed. It can go up to 300 kilometers per hour. And this cyclone moves at an average rate of 300 kilometers per day. So people get confused between the movement and the wind speed associated. The wind speed associated is the wind which is rotating around the center of the cyclone. And the movement of the cyclone is the rate at which the cyclone is moving from one place to other place. Now, if you just look at this particular cyclone, you will find that it has got 4 parts. At the center, there is a circular area which looks like blue, and this is called as eye of the cyclone. The blue area stands for the clear sky. That's there is no convective cloud, very limited clouds. If it is daytime, if eye is there in your area, you can see the sunlight. If it is nighttime, you can see the stars. Around the eye, there is a very deep convective cloud, just like a wall surrounding the eye. That is called as eye wall or wall cloud region. This wall cloud region is about 20 to 100 kilometers width. It is the most disastrous region. There you can have the maximum wind, maximum rainfall, and maximum devastation takes place in that area. Pressure gradient is maximum, temperature gradient is also maximum there. So therefore, you get heaviest precipitation and strongest wind in this wall cloud region. Whereas in the eye region, you will have the calm wind and the clear sky. So if you can manage to move along the eye, then you will be safe if you are associated with the cyclone. But it is very difficult to move along the eye because eye is so small. Cyclone shows some kind of sometimes zigzag motions. So therefore, the area where eye passes, you will find that at first there will be the front part of the wall cloud region, and again there will be limited period, calm wind and clear sky conditions. Thereafter, the rear part of the cyclone will come. There will be again devastating winds and rainfall. So therefore, the area where eye passes, that area experiences the most disastrous weather because of the heavy rain, wind, and storm surges, as the cyclone is encountered by the wall cloud region twice over that region. Now, if you just look at how do we define these tropical cyclones over North Indian Ocean, you will find that, as I told, the tropical cyclone develops from a low pressure area, and this low pressure area is defined as the area where pressure is low compared to the outermost surroundings. So in that case, what happens is that when there is a low pressure area, the wind from the high pressure area blow towards the center of the low pressure area. So while blowing towards the center of the low pressure area, they cannot move straight. Because of the rotation of the Earth around its own axis, the winds are deflected towards the right in the northern hemisphere and deflected towards the left in the southern hemisphere. Therefore, when the wind blows from high pressure to low pressure, it moves in anti-clockwise direction and makes a wave. So in a low pressure area, therefore, you get a cyclonic circulation of the wind. In case of high pressure area, you will get an anticyclonic circulation of the wind. So as the pressure falls gradually, if there is favorable conditions, the low pressure area becomes a depression. According to the wind speed increases, and wind speed becomes 31 to 49 kmph. Further, if it becomes a deep depression, wind speed further increases, becoming 50 to 61 kmph. Like that, if it becomes a cyclonic storm, wind speed becomes 62 to 88 kmph. Severe cyclone storm, 89 to 117 kmph. Very severe cyclone storm, 118 to 166 kmph. Extremely severe cyclone storm, 167 to 221 kmph, and super cyclone storm, 222 kmph and above. But for your sake, if you want to remember, you can remember like this. Approximately, cyclone storm means 60 to 90 kmph. Severe cyclone storm, 90 to 120 kmph. Very severe cyclone storm, 120 to 160 kmph. Extremely severe cyclone storm, 160 to 220 kmph, and super cyclone storm, more than 220 kmph. Just for easier remembering, I just tell the approximate values. So this classification is different for different ocean basins because they have adopted different ocean basins. Nobody reconciles, and worldwide you will find that there is a difference in nomenclature of the classifications. But however, the definition of the tropical cyclone, that is the wind speed exceeding 34 knots or 62 kmph, is same worldwide. Now, if you just look at this cyclone in radar, I have got two pictures here. On the left side, you have got an analog radar where you find only the reflectivity of the cloud. It is in black and white picture. It was earlier one taken by IMD. And the right hand side, you have got Doppler radar picture of a tropical cyclone. In both the cases, you can find out the eye of the cyclones and the spiral bands. You can find out the wall cloud region, and also you can find out the outer streamers. So with the help of this Doppler radar, we are having the benefit of analyzing not only the reflectivity in the clouds due to the clouds, but also we can find out what is the precipitation associated with the clouds. We can also find out what is the wind distribution in the tropical cyclones. Now, this tropical cyclone, as I told you, it develops from a low pressure area. Just like if you just look at this picture, the top one, I have written here the tropical disturbance or low pressure area, you will find that convective clouds are not organized. They are just scattered and distributed over an area. When it becomes a depression or deep depression, just go to top and right picture, there you will find that the clouds are taking a shape. They are becoming organized, not fully organized, but they are getting organized. So that is a depression. Now you come to the third picture in the bottom left. There you find that it is more organized. It's the cyclonic storm. And the rightmost in the bottom, you will find that the very severe cyclone storm is better organized. Eye is seen, wall cloud is there, spiral bend is there. It has got all features. So like this, a low pressure area gradually evolves into a tropical cyclone. Now, if you look at the life cycle of the tropical cyclones, you will find that the entire life cycle can be divided into 4 stages. The first stage is called as the formative stage, as I discussed. It takes about a few days for a low pressure area to gradually become a depression. Thereafter, it is immature stage where depression gradually intensifies into deep depression, cyclone storms, severe cyclone storms, etc. It takes about half a day to 2 to 3 days. Then the mature stage. In the mature stage, there will be no increase in intensity. Intensity remains same. At the same time, the size of the cyclone increases. It becomes bigger in size. So this period is half a day to about 2 to 3 days. After getting the maturity, either it crosses the coast and decays, or it comes in contact with cold water, it decays, or the atmospheric situation becomes adverse, leading to decay of the systems. Or sometimes another cyclone comes in and 2 cyclones interact. One cyclone strengthens, other cyclone weakens. This is called the Dvorak effect. However, so decay stage starts. It takes about 2 to 3 days to decay from the highest intensity to a low pressure area. Now, if you look at the structure, horizontally, as I told you, it has the extension of 100 to 1000 kilometers, and the average it is 500 kilometers. Vertically, it is about 15 to 18 kilometers. You can find out how the wind in the leftmost diagram in the left hand side, you can see how the wind is rotating around the center of the cyclones, just like a coiling of a snake in the snake charmer's basket. So therefore, Henry Paddington, when he discovered this weather phenomena over the Bay of Bengal, he found that wind is rotating in anti-clockwise direction, just like the coiling of a snake. So he took the word cyclos from Greek and told it as the cyclone. Therefore, credit goes to British India for naming this particular weather event as cyclone. And you find that the cyclones usually move towards northwest. It is because of the rotation of the earth. Cyclones usually move towards northwest. But you will find sometimes they change the track and they go to some other directions because it depends upon the steering flow or the wind in which the cyclone is embedded. See, these are some of the pictures how the winds are rotating not only at the surface but also they are rotating and going off to the upper troposphere. So vertically, you can have 3 different layers. One is the inflow layer, which is up to about 3 kilometers. Then you've got the middle layer where you don't have inflow, minimum inflow. Then you've got the outflow layer where maximum outflow is there. So you've got 3 different layers and 3 different mechanisms of inflow and outflow in the vertical structure of the tropical cyclones. Now, if you look at the wind distribution and pressure distribution in a cyclone, you will find that at the center of the cyclone, wind is calm, wind is almost nil, you can say. And wind sharply increases and becomes maximum in the wall cloud region. Mostly in the middle of the wall cloud region, wind becomes maximum. And if you see this picture, the blue line indicates the wind distribution at the surface. You will find that the right-hand side wind is slightly higher than the left-hand side. Therefore, when the cyclone crosses the coast, the right-hand side of the track experiences more winds and hence the more storm surge and more devastation as compared to the left-hand side. The red line is the pressure. You will find that pressure is lowest at the center and pressure gradually increases as you go away from the center. Now, this is the wind distribution on the left-hand side around the center of the cyclone. You find that wind is not maximum at the surface. Wind is maximum at the top of the boundary layer. About say 1 kilometer, 1.5 kilometer. Wind is maximum, and thereafter, if you go off, wind gradually decreases. Similarly, horizontally, wind gradually decreases as you go away from the cloud region towards the outermost layer. Considering the temperature distribution in a tropical cyclone, you will find that it is warmest at about a height of about 10 kilometers or 300 hectopascal. The cyclone is a warm core system. Entire central system is warm. The eye is warmer compared to the surroundings. Warmer the eye, stronger is the system. And maximum warming takes place at 300 hectopascal or at 10 kilometers. Sometimes, apart from the single eye, what we discussed so far, you will find that there will be double eye. In this picture on the right hand side, you can find that there is an inner eye. Surrounding that, there is a black ring that is called the inner eye wall. Thereafter, you will find that there is a white area that is called as the outer eye. And after the outer eye, you will find again another cloud that is dark area, that is black area surrounding. That is called as the outer eye wall. So that means sometimes you will get the double eye wall structure of the tropical cyclones. Recently in Odisha Super Cyclone 99, we have got double eye wall structure. In Cyclone Phylline also, we have got the double eye wall structure. So when this double eye wall structure is noticed, it is sure that system is intensifying. And maximum intensity occurs at that time when double eye wall structure is well defined. After that, what happens actually, because of the double eye wall, the air from the outside cannot venture to go into the inner eye region. Therefore, gradually inner eye and inner eye wall region gets cut off from supply of moist air from the surrounding. As a result, the inner eye wall gradually disrupts or collapses, and the inner eye merges with the outer eye. So therefore, it becomes a bigger eye. So that is indication that when this process takes place, that means collapsing of the inner eye wall and merging of inner eye with the outer eye becomes bigger, single eye. In that process, the cyclone weakens. So after that, again, if it is in the favorable conditions, it can further intensify and you can have further intensification of cyclones. So what you find actually, there is a cyclic process during the formation of the double eye. It is a first single eye. From the single eye, you are going for the double eye structure, that is intensification. And once you have a double eye structure, the maturity takes place. Then after that, the double eye structure, the inner eye collapses, and the inner eye wall collapses, and inner eye merges with the outer eye, and single eye forms. This entire cycle is called as the eye wall replacement cycle. While the first half of the inner eye wall replacement cycle, you have got the intensification of the system. In the second half, you have got the weakening of the system. Now people sometimes ask, what is the difference between tropical cyclones and extratropical cyclones? If you look at the tropical cyclones are the atmospheric disturbances which mainly occur because of the latent heat released because of the condensation of the convective clouds at the upper troposphere, say 500 to 300 SPA. Whereas the mid-latitude or extratropical cyclones extract their energy from the horizontal gradient of temperatures. Say, for example, if you ask me what is the temperature difference between say Sri Lanka coast and Bengal coast, West Bengal coast, hardly you will find a difference of 1 to 2 degrees. But if you see the temperature difference between Moscow and Delhi, you will find that there is a large temperature difference of about 20 to 30 degrees Celsius. So this large temperature difference in especially the winter season leads to the extratropical cyclones, whereas this minimum temperature difference over the sea area with the development of the convective clouds leads to the tropical cyclones of sea areas. So therefore, tropical cyclones are the barotropic processes where you don't have horizontal temperature gradient, whereas mid-latitude cyclones are the large temperature gradient processes or baroclimatic processes. So in the tropical cyclones, you will find that strong wind occurs near the surface, therefore it is more devastating. But in case of mid-latitude or extratropical cyclones, strong wind occurs at a height of 8 to 12 kilometers, therefore it is not devastating. The tropical cyclones are warm core systems, whereas mid-latitude cyclones are cold core systems. So there are two imageries. Right hand side is the tropical cyclone, left hand side is the extratropical cyclones. And similarly, people also ask what is the difference between tropical cyclone and tornado. See, both tropical cyclones and tornado or thunderstorms are the atmospheric fluids, but they have little in common. Tornadoes have a diameters of a few tens to a few hundred kilometers. They are produced by a few hundred meters. They are produced by severe thunderstorms in presence of strong convective instability and variation of wind with altitude. So that means there is a high vertical winds here. But in case of tropical cyclones, the diameters are hundreds of kilometers. That means tropical cyclones are large scale systems, whereas tornadoes are micro scale systems. In the tornado, there is variation of wind with height, whereas in case of tropical cyclones, there is less variation with height. In case of tornado, you've got convective instability, whereas in case of tropical cyclones, you've got neutral convective instability. So these are the few differences between tropical cyclones and tornado. On the right hand side is the tropical cyclones, the left hand side it is the tornado image. Now, if you just look at the climatology of tropical cyclones, you will find that about 80 cyclones develop throughout the world. Out of 80, we have got about 5 cyclones in a year. That means North Indian Ocean, including Bay of Bengal, Arabian Sea, do not experience many cyclones. It's only 7% of the total number of cyclones in the world. But however, if you just look at number of deaths, you will find that it has been notorious for the highest number of deaths. Of course, fortunately, and with the various initiatives taken by the Government of India, including Minister of Earth Sciences, the number of deaths have been reduced in recent years. And out of 5 cyclones, we have got 3 severe cyclones. Similarly, in the entire ocean basins of the world, out of 80 cyclones, we get about 35 to 40 severe cyclones. The Northwest Pacific is the most prone for tropical cyclones, then followed by the North Atlantic. Now, if you look at North Indian Ocean here, Bay of Bengal is more prone for tropical cyclones compared to Arabian Sea. Out of 5 cyclones, usually we get 4 over Bay of Bengal, 1 over Arabian Sea. Again, unlike other ocean basins, our ocean basin shows bimodal character. That means we've got 2 cyclone seasons. One is April, May, June, other one is October, November, December. Considering months, you will find that May and November are the most prone months for the tropical cyclones. If you compare Arabian Sea and Bay of Bengal, tropical cyclones of Bay of Bengal are more disastrous. It is mainly because of the bathymetry of this coast. The storm surges can be expected higher over the Bay of Bengal region, especially in the North Bay of Bengal, including North Odisha, West Bengal, and Bangladesh. Now, if we just look at what are the parameters which govern the genesis of the tropical cyclones, you will find that the tropical cyclones usually develop because of the 6 parameters. Out of 6 parameters, 3 are thermal parameters like ocean thermal energy, relative humidity, and instability in the atmosphere. And 3 are dynamical parameters like Coriolis force, then low level relative verticity, then inverse of tropospheric vertical wind shear. That means if you have got higher ocean thermal energy or higher sea surface temperature, you can just look at the right side diagram, then it becomes more favorable. So this is the energy trapped in the upper part of the ocean. If it is more warm and more energy is there, it will help in genesis and intensification of cyclones. The Coriolis force, just right side diagram, if you just look at, you will find that the cyclones do not develop near the equator. Usually it develops to the north of 3° north, and maximum it occurs in the tropical belt. Towards the extratropics, also you will not have the cyclones because of the colder sea and other unfavorable conditions. So therefore, basically you will find that near about 15° north in both the hemispheres, the number of tropical cyclones genesis is a maximum. And as the latitude increases, Coriolis force becomes favorable for genesis of tropical cyclones, but not near the equator. Minimum Coriolis force is required for development of tropical cyclones, which is not available near the equator. Similarly, the relative vorticity. Vorticity is nothing but a measure of the rotation around its own axis. So if you have got a cyclonic vorticity, that means it has got the capacity to rotate around its own axis in anti-clockwise direction, it helps the genesis of the tropical cyclones. The third one is the vertical wind shear. It is the difference of wind in the lower level and the upper level. If the difference of wind in lower level and upper level are less, it becomes favorable for genesis of tropical cyclones. If difference of wind between lower level and upper level is high, it becomes unfavorable for genesis of tropical cyclones. So these are the same thing. I just wanted to show you in one diagram in the cyclones, which are the forces which is working. You have all these forces working together for genesis and intensification of the tropical cyclones. Okay. So what you find actually, the cyclones are developing over the sea surface, and over the sea surface we have got very limited data. So therefore the tropical cyclone monitoring basically depends heavily on the ocean observations, and these ocean observations are taken off in two ways: direct ways by putting off the buoys and SCATSAT, etc., ships, and indirect way is the measurement with the help of the satellites like SCATSAT and also with the geostationary satellites. Now, if you look at the movement of the tropical cyclones, I used to say that the tropical cyclone is just like a cork in the ocean. If you just throw a cork in the ocean, that cork will float and will move in the direction in which the ocean current is. Similarly, in the atmosphere, the cyclone will move in the direction where the wind is blowing. That means the column of the atmosphere in which cyclone is embedded. You can see in the diagram at the top. The column of the atmosphere in which the cyclone is embedded, that decides the movement of the cyclones. If wind is blowing from east to west, then cyclone has to move from east to west. But this wind has to be decided in the entire column in which the atmosphere in which the cyclone is embedded. But apart from that, there are other factors also which determine the movement of the systems. For example, the beta effect. Beta effect is nothing but the rotation of the Earth around its own axis. This rotation itself leads to north-westward movement of the cyclones. But there can be influence of the environment, as I explained you about the atmosphere in which cyclone is embedded. But sometimes there will be trochoidal motion, zigzag motion of the cyclones. And sometimes the two cyclones can interact with each other. So if one cyclone is moving towards north, other will move towards the south. That is called as Fujiwara effect. So at the same time also there are other parameters which influence the movement of the tropical cyclone. Similarly, the intensity, if we just look at, actually since the cyclone is developing over the sea surface, intensity estimation is also difficult because of the lack of data. So therefore, it is very difficult to find out or assess the initial condition of the cyclones. But however, with the advent of the satellites, the advent of the buoys, ships, etc., we have been able to have the realistic estimates of intensity in recent years, and hence the better intensity forecast also. So if we just look at, there are various forces acting in the cyclone. For example, in different layers of the atmosphere, there are clouds, so there will be cloud-like interactions. So there will be the cyclone structure is called storm scale interactions. And there will be environmental structure. In the environment, there will be upper level winds, there will be drier intrusions, there will be wind shear. There are many factors, environmental factors. So all these atmospheric and oceanic environment factors, they determine the intensity. And also the storm scale forces like the eye wall, spiral bands, etc., they also determine the intensity. And also the interaction within the cloud itself, the convective scale interaction also determine the intensity. Therefore, sometimes you will find worldwide that intensity is too hard for the forecasters to provide the forecast. But however, over the years, there has been improvement, but still worldwide, we have to go a mile further to improve the intensity forecast. Now, if you look at what intensifies the PCs, you will find that there are various processes which influence the intensity. Just like the genesis parameters, we find that all the genesis parameters are important to determine the intensification of the cyclones. But what weakens the TC? The TC weakens, tropical weakens when it moves over the land. Or if it is influenced by the strong vertical wind shear, or if it is restricted by the outflow, or if it is entering into a ocean where you have got cooler sea surface temperature, or otherwise if the cyclone is moving slowly. If the cyclone moves slowly, it gets drained out because of the precipitation, and the sea surface there also becomes cooler. Therefore, it does not get maximum energy. Or otherwise, if there is a cold, drier intrusion into the middle and upper troposphere of the cyclones, or if there is a fast DC motion also. So all these conditions also lead to the decay of the tropical cyclones. So therefore, critical element while analyzing the various features for cyclone forecast is to monitor continuously, update yourself about the current status of the atmosphere and ocean, and examine all the parameters with respect to movement and intensification of the cyclones. Now, knowing all these features, now we should know how to mitigate the cyclone hazards. For mitigation of the cyclone hazards, there are various approaches. The first one is that we should know what is the hazard associated with the cyclones. That means the first and foremost step is to analyze the hazards. Then to have a vulnerability analysis. The same cyclone crossing different parts of the country may not have the same impact because of the different vulnerability in different coasts. So that we should know the socioeconomic vulnerability, we should know the physical vulnerability, we should know the awareness of the public, awareness of the people by which it's going. We should know the preparedness of disaster managers. Then we should know the planning of the disaster managers. This is also required, preparedness and planning. Then early warning and mitigation. However, if you look at all these components, there was a survey in South Asian region which is found that early warning is a major component, because as you know, you cannot change the structure. Damage to the structure cannot be avoided, because you cannot change the mud house to pakka house within a day or within 1 year, all the houses in the country. But if you can provide early warning, the action can be taken to shift the people from mud house to pakka house and hence save the lives. Therefore, early warning is a major component. And therefore, India Meteorological Department, Minister of Science, has always tried to improve the early warning, to provide skillful monitoring and prediction of the cyclones, and to provide effective warning products generated and disseminated. And also we go for coordinating with emergency response units. And also we try to change the public perception. We try the public to believe the cyclone forecast issued by India Meteorological Department. So these are the various processes in early warning system of tropical cyclones. We take all the observations as it is data sparse region of the sea. We don't spare any observations. We take all available observations while analyzing the tropical cyclones. It is space-based observations, upper air observations, and surface observations from automatic stations, rain gauges, synoptic observations, buoy observations, aviation, ships, etc. And also the geostationary and orbiting satellites, radar observations, aircraft observations. All these observations help the forecast to define the initial status, to find out whether it is a cyclone, whether it is a low pressure, whether it is a depression, etc., and where it is located, what is its structure. At the same time, all these observations are fed in a digital manner into an array of numerical weather prediction models. And these models are run twice or 4 times a day, and forecast is generated. And this digital forecast is converted into a public language, which is called as the end forecast. And in this end forecast, not only provide the forecast and warning, but also we say what is the impact of the cyclone, what action to be taken. So it becomes an end-to-end bulletin, and that puts decision makers for various decisions. All these diagrams given hereby are the various processes associated with the tropical cyclone monitoring and forecasting. Now, just going a little, if you look at the observing systems, we have got various types of observing systems, but if you go, the coverage, the satellite has got the highest coverage, but the confidence of satellite observation is low. The most confidence observation is the domestic synoptic data, which is taken as the ground truth. But however, you cannot have the ground truth over the sea. Therefore, when there is a cyclone over the sea, we depend mainly on the satellites. When it comes closer, it depends upon the radar. When it becomes more close, and we depend upon the actual observations along the coast. So by that way, we utilize all types of instrumental observation tools like satellite, radar, spectrometer, and automated weather stations, our departmental observatories, ships, buoys, etc. Now, in the satellite, all of you might be knowing that there is a scale called as Dvorak technique, that is key number, and key number is a pattern technique where we define the intensity in the scale of 1 to 8. If it becomes 2.5 key number, we say that it is a cyclone. If it is, for example, 5.0, we say it is an extremely severe cyclone storm. If it was 6.5, we say that it is a super cyclone storm. But determining all this location intensity, therefore, it is a finally agreed official location intensity utilizing all the informations together. So therefore, worldwide, it is called as the best track and best intensity of the cyclones. Now, while doing this center and intensity fixing of the cyclones, we follow a standard operating procedure. We consider all the database. From database, for example, first we go to visual and IR imagery of the satellite. We apply the Dvorak technique, find out the location and intensity. Then we go to look into the microwave imageries from various polar orbiting satellites. We make the corrections or modifications. Then you look into the radar image. You take the level 3 corrections. Then you look at all the synoptic data available from ships, buoys, coastal stations, island stations, etc. We go for the level 4 corrections. Then after that, we optimize all these informations and smoothen the track and check the consistency. And finally, we define the best track position and intensity of the tropical cyclones. So in addition to all these short and medium range monitoring and forecasting, also we go for extended range forecasting. As you know, in the recent years, we are providing 2-week forecasts of the cyclones. So this is an example of 2018, 22 April, we started this prediction, actually extended forecast. On 27 September, we issued the prediction that a cyclone is going to develop over the Arabian Sea in the second week. On 4th October, we told that there are going to be 2 cyclones, and one in Bay of Bengal and Arabian Sea. If you remember, the Titli and Luban were the 2 cyclones simultaneously developing over Bay of Bengal and Arabian Sea. So like this, the extended forecast for 2 weeks are helping the disaster managers to make a preparedness. They're getting a higher lead period for the preparedness and planning. So this is the forecast of Genesis. We provide 5 days in advance. So what we do actually on daily basis, we provide a bulletin called as tropical weather outlook. There we say what is the probability of genesis of a depression. Cyclogenesis means formation of a depression over Bay of Bengal and Arabian Sea. And if there is a probability that is calculated based on the various numerical weather prediction model guidance, we say whether there is a low probability or medium probability or high probability, and accordingly we provide the informations. Now, for track and the movement of the forecast, movement forecast of the tropical cyclones, the India Meteorology Department and Ministry of Earth Sciences have come off a long way. At present, you will not believe, we have got about dozen models, dozen numerical prediction models. 7 models are run within the ministry itself, and 5 models are accessed with a bilateral understanding with different international countries. Along with these numerical prediction models, also utilize satellite, radar, and other climatological information and synoptic information to provide the forecast. The track and intensity forecast provided by India Meteorology Department is an objective consensus forecast utilizing a decision support system. So similarly for the intensity forecast, we have got the various numerical prediction models, and also have got the dynamical statistical models for intensity and rapid intensifications and decay of the systems after landfall, etc. So all these are taken together to provide the intensity forecast. So this is just an example of the cyclone Fani, which crossed Puri on 3rd May 2019, and you'll find that how the model is helping us. In the right hand side, this is the IMD GFS model. This is a global model which is providing forecast how the cyclone is evolving and it is crossing on 3rd May near Puri. On the left hand side, you'll find that there are various tracks. These tracks are from various types of numerical prediction models. You'll find that initially the tracks will be different from each other. There will be large divergence. Gradually, as you come closer, the tracks become consistent, they become closer to each other, and hence the confidence increases. So all these multimodal ensembles and single model ensembles are utilized to develop a consensus forecast of the track and intensity. So this is just an example of the cyclone filing. You will find that how sometimes the forecasters are confused because of the guidance of the numerical models. On the left hand side, you'll find that this is 108 hours before the forecast, where you find that the tropical cyclone track forecast by different models are almost consistent, closer to each other. On the other hand, 84 hours before, you find that the tropical cyclone track forecast for the same cyclone is becoming scattered. So that means there is low confidence among the models now as you move from 108 hours to 84-hour forecast. But however, here comes the knowledge, experience, and expertise of the forecaster, and that objective comes subjective decision-making process. And finally, if you remember, for the filing 5 days ahead, we told it to cross Gopalpur, and it crossed Gopalpur also. So therefore, I will say that the tropical cyclone forecasting, it is a man and machine interaction. The objective consensus derived from numerical weather prediction models are modulated by the subjective consensus derived from the exchange of knowledge, experience, and expertise of the cyclone forecasters on real time. So this is another example. You can find that you have got 2 tracks moving towards Andhra Pradesh and 4 to 5 tracks moving towards Odisha. Now the point comes whether to go for Andhra Pradesh. To solve these problems, we came up with the ensemble prediction systems. If you go to ensemble prediction system, what you find actually hardly any member of the ensemble is moving towards Andhra Pradesh. All are moving towards Odisha. So this is the advantage of ensemble prediction system compared to single model, which can be utilized to provide most probable track and intensity forecast. So finally, utilizing all these, we provide the forecast. This is the example of the cyclone Fani, which was crossing Puri. We provided forecast continuously for Odisha coast from 29th onwards. We told that it's moving to Puri. And as a result, action was taken by the concerned state and central government agencies, and number of deaths was minimized. So you can hardly find that black line and red line differing from each other. The red line is the forecast line, and black line is the actual track of the cyclones. What do you find actually? The forecast track has been very consistent, and the forecast track has been almost same as the actual track, enabling the disaster managers to have the confidence on the forecast and utilize it for evacuation and other measures to minimize loss of lives and properties. Now, coming to the disasters weather associated with the tropical cyclones, you will find that, as I told in the beginning, we have got the heavy rainfall, gale wind, and storm surge. The storm surge occurs on the right-hand side of the tropical cyclones, as you can see from this diagram. And if you look at India coast, you'll find that there are three specific belts. One is the North Odisha, West Bengal area, where you get the maximum storm surge. Storm surge is nothing but the abnormal rise in sea level because of the approaching cyclones near the coast. It's just the tidal wave above the astronomical tide. There is a notorious record of 13 meters of storm surge over Hooghly River on 7 October 1737. In Odisha super cyclone, it was about 5 to 6 meters above the astronomical tide. In the recent cyclone Amphan, it was 4 to 5 meters over south and north central Pargana district of the West Bengal. The second front area you can find out in the central part of Andhra Pradesh, near about Machilipatnam, where also you get maximum storm surges. And third one is near about the Pamban area, and that also in Tamil Nadu coast you get more amount of storm surges. Now, for this storm surge purpose, there has been many approaches, starting with some kind of nomogram. We have come up with the storm surge and inundation model. In association, the INCOES runs the model for providing the storm surge forecast and coastal inundations that is utilized by India Meteorological Department to tell what will be the extent of inundation, what will be the height of inundation in different parts of the coast when cyclone is crossing the coast. This is just an example of cyclone Fani associated storm surge near Odisha coast. Similarly, for rainfall monitoring and forecasting, we have got various tools. We have got the various types of inputs from satellites, radar, and observations. We have got about 4,500 rain gauges which provide the information for monitoring of the real-time cyclones. What we did actually in the Ministry of Earth Sciences, we merged the data of the satellite and the rain gauges to provide on the right-hand side picture the merged rainfall data, because the cyclones cannot be monitored with the rain gauges when it is of the sea, and this information is very much required for monitoring and forecasting purpose. In the right-hand side diagram, that is the merged data in association with the tropical cyclone Fani. Also, we have got various types of numerical prediction models which provide the forecast and hence the heavy rainfall for different river catchments when cyclone is passing the coast. So to carry out all these processes, you need a decision support system. This is just a glimpse of the decision support system which we have in India Meteorological Department to compare, comprehend, and analyze all types of observations and the forecast products from various types of numerical prediction models, and finally to take a consensus decision and prepare the forecast products and warning products and disseminate it to the last mile. So this is in nutshell all the processes you can find out in case of cyclone Fani. We have got the satellite, we have got the radar, then we have got the numerical prediction models, then we have got the multimodal tracks, then we have got the final forecast track and forecast intensity, then forecast rainfall and forecast storm surges. So to carry out all this warning process, in India, we have got a well-defined cyclone warning organization. We have got a cyclone warning division at headquarters, New Delhi, and we have got 7 cyclone warning centers across the west and east coast. And considering the capability of India Meteorological Department, World Meteorological Organization recognizes IMD as a regional specialized meteorological center for tropical cyclones, and we are responsible to provide the tropical cyclone advisories to all the countries in the Bay of Bengal and Arabian Sea region. It includes 13 countries from Bay of Bengal and Arabian Sea. Also, we provide the global maritime distress support system under the WMO network. At the same time, the cyclone also have the impact in the aviation sector. Therefore, we also act as a tropical cyclone advisory center for international civil aviation, and we provide guidance every 6 hours during cyclone period to all the countries in Asia Pacific region for smooth aviation purpose. These are the sector-specific warnings. You will find that there are about 9 types of warnings being issued by India Meteorology Department every 3 hours when cyclone is approaching coast. Actually, these warnings are designed in such a manner that it meets the requirement of each sector, like sea area, then coastal area, then for Indian Navy, then for fishery, then for port, aviation, for public, for disaster managers, etc. And all these warnings are provided in different stages. We provide the first information called as the pre-cyclone watch. Then we provide the cyclone alert. Then we provide the cyclone warning. Then we provide the post-landfall outlook. And finally, when the cyclone weakens, we give a de-warning. And in addition to the information provided in the cyclone warning, also we provide information about the damage expected with the tropical cyclones and what action is to be taken by the general public and disaster managers. This is given in different stages of the tropical cyclones, like deep depression stage, cyclone storm stage, severe cyclone storm stage, very severe cyclone storm stage, extremely severe cyclone storm stage, and super cyclone storm stage. The damage such prepared based on the historical damages of the different tropical cyclones. Now, also we give different color codes for different warnings, like cyclone alert we give yellow message, cyclone warning orange message, and post-landfall outlook as the red message, as per the requirement of the National Disaster Management under Ministry of Home Affairs. Now, you'll be happy to know that we also have the advanced tools for disseminating all types of information. We maintain redundancy because in case of cyclone, you cannot depend upon only one channel of information. So we maintain redundancy. Also, we've got a dedicated website that is called RSMC website, RSMC New Delhi website. And you will find that from each cyclone, the number of visitors to the website is increasing and the number of hits are also increasing. You can just imagine, in case of Fani, it was more than 250,000 people who visited on a particular day, that is 3rd May, when cyclone was hitting the coast. Now, if you look at what is the way ahead, yes, there are still gaps in technology vis-a-vis the capability of Minister for Sciences and India Meteorological Department. We are all working together. The product, whatever you see today, it has been possible because of the cohesive approach by all the constituents of Minister for Sciences, including India Meteorological Department, Indian National Center for Ocean Information Services, Indian Institute of Tropical Meteorology, National Center for Marine Weather Forecasting, National Institute of Ocean Technology, and many others. And also, there has been some effort by the many academic and R&D institutes within the country and outside under various umbrella schemes. So as a result, we have come up with this development, but still there are certain gaps with respect to the scientific understanding, with respect to, for example, detailed structure and dynamics of tropical cyclones, interaction between cyclone, ocean and surrounding environment, internal physical and dynamical processes in the clouds. It is basically because we don't have the aircraft reconnaissance in this region. So therefore, we don't know actually what are the processes being carried out within the cloud itself or within the wall cloud region itself. So gap in observational modeling systems of forecasting the high spatial resolutions. There is also scope. We have come up with the resolution of 12 kilometers in global models and 3 kilometers in the regional model, but there is still scope to improve the resolution of the model and the physics of the model based on the observational schemes, enhanced observational scheme. So there is also scope to improve the forecast skills. We have come up a long way. We are now second to none in terms of forecast accuracy, but still we have kept a target that by 2030, we will have the landfall forecast error of about 30 kilometers, which is currently about 45 kilometers. So MoES is continuously upgrading its plan and strategy for all the above. Each and every cyclone is documented and it is published in the website. It is circulated to disaster managers. It is given to general public and media. We also learn lessons from each and every cyclone and past cyclones. All these lessons are documented and these are addressed for the next cyclones. So by that way, India Meteorology Department and Ministry of Sciences is moving from step to step, from one cyclone to the other, with improved monitoring, improved modeling, improved forecasting, and improved early warning services. So this is one of the important targets in the next 5 years, that we will go for impact-based forecasting from static to dynamic. For this purpose, we have to integrate the information hazard, especially cartographic, geological, hydrometeorological, and geospatial data, vector, and raster. We have to go for exposure information like GIS and geospatial infrastructure settlements and land use. Then vulnerability assessment with statistical sensors and survey data. And then finally, we'll find out the value at risk considering the impact. So to do that, already NDMA has taken the project called as National Cyclone-Based Mitigation Project, where IMD is also involved and all state governments in the coast are also involved. A dynamical impact-based forecast early warning services scheme is being adopted, and I'm sure in next 1 or 2 years, we will have a dynamical impact-based forecast and risk-based warning in case of the cyclones and other severe weather events. Thank you very much for listening me with patience.
Thank you, sir. Thank you very much for a very detailed webinar on tropical cyclones with basics to observations to prediction. So thank you for sparing your valuable time for MoES webinar too. So we have kept some questions for you, sir, in the chat window. So kindly come to the video mode and read the question and answer.
Okay. So first question, what I find actually, what were the specific parameters in the cyclone advanced warning system that improved after the Odisha super cyclone? If you compare the early warning system at present with the early warning system in 1999 Odisha super cyclone, you will find that there has been a paradigm shift in each and every component of early warning system. Now, considering the first one, the monitoring, you will find that at present, we did not have the Doppler radar, we did not have the buoys, we have limited ships, we have got only one satellite, we do not have the scatterometer data from India, whereas we have now three satellites. One is INSAT 3D, INSAT 3DR, and SCATSAT. We have got all Doppler radars along east and west coast, and also we have got 20 buoys over Bay of Bengal and Arabian Sea. We've got about 30 ships equipped with automated weather stations. We've got automated stations in every 30 kilometers along the coast. So therefore, there has been enhanced observation network to define and monitor better. Similarly, if you look at the models, at that time there was only one model, limited area model, with the forecast up to 48 hours. And that forecast was not available in real time. It was taking about 12 hours to run the model. And forecast was not consistent, not accurate. It was not usable. Whereas at present, Minister for Earth Sciences have 7 models which are run with our high power computing system. At that time, there was no high power computing system as such to carry out all these model performances. And also, we have got a lot of derived products from these models. In addition to that, we have got another 5 models from different countries. So about a dozen models are being analyzed every day twice to find out the cyclone forecast. Similarly, if you just look at the forecasting, at that time there was no decision support system. The data were coming in a teleprinter or telegram. It was taking about 3 hours to get the data, another 2 hours for taking to plot the data manually, and then for analysis also forecast was taking about 1 hour. So by that way, it was taking about 6 to 8 hours to prepare the forecast based on the initial condition of, say, for example, 5:30 morning observations. So by the time the forecast is prepared, it becomes around 2:30. But in the present scenario, the observation data is received with the dedicated communication channel within 10 minutes. And it is also automatically plotted and analyzed, and it is corrected by the forecasters. And for the decision making also, we have got an objective decision support system. Therefore, it has improved the quality, it has improved the accuracy, and also improved the timeliness in the early warning. Similarly, for early warning dissemination, at that time, we used the telegrams. Say, for example, if you send a telegram to district collector, it was taking 4 to 5 hours. By that time, the cyclone might have moved about 200 kilometers. Therefore, people felt that cyclone has moved. Thereafter, IMD is telling that cyclone is coming. But that was actually because of the delayed communication, because of the deficiency in the communication system. But now we have got very high effective information technology where immediately we utilize all types of media, including social media, to reach out to the last mile about the tropical cyclone forecast and warning. Now, as a result of all this, there has been improvement in monitoring, forecasting, early warning, and also the accuracy and service delivery of India Meteorological Department. Now, second question, what are the physical and dynamical reasons for occasionally hitting tropical cyclones at the time of southwest monsoon? Yeah, usually southwest monsoon period is June to September. But if you just look at the main monsoon months are July and August. Sometimes you will find that cyclones develop in June and September in the onset phase and withdrawal phase, because it is the transition phase, the cyclones can develop, as I have discussed earlier. But you will find sometimes, as you told, that common cyclone developed in July. It is not August, but July 2015.
Yes, sometimes during the process, it was a marginal cyclone. It cannot become intense cyclone. It is a marginal cyclone. It developed over the central Bay of Bengal. It moved towards the coast in the North Bay, and it got a little more time. And at the time, vertical winds was favorable. So, if in general the environmental conditions are not favorable during monsoon season, mainly in the month of July and August, for development of the cyclones, but sometimes there can be the opportunity where the atmospheric conditions will be favorable to make it a marginal cyclone. We are not expecting very severe cyclone storm during main monsoon months of July and August. Now, what is the mechanism which makes the I region calm, whereas I1 is a region of intense convection? Yeah, if you just look at the structure of the tropical cyclones, the I region, which is a diameter about 10 to 50 kilometers, here there is a subsidence of air. So what happens actually, as per the mechanism of tropical cyclone development, the air moves from the high pressure cell towards the low pressure cell. Cyclone develops from the low pressure cell. Pressure is lowest at the center. While it moving, there will be upward motion in the wall cloud region. While it moves upward motion, there is a secondary vertical circulation in the wall cloud region. The secondary vertical circulation in the wall cloud region leads to subsidence in the center of the cyclones. And this subsidence means the air moving from the top to the bottom. As I told in my one of the slides, that it is warmer at the 300 hectopascal or 10 kilometer height, and that air is warmer, it is moving down. And moving down also, it comes warmer. Therefore, in the central region, you will have relatively warmer air compared to the surroundings. Then question is, what determines the area or radius of the cyclone I? This area or radius of the cyclone I is determined by many factors, especially the factors determining the intensity of the tropical cyclones. See, if the intensity is increasing, the wall cloud region becomes more compact and I becomes smaller and smaller. If intensity is decreasing, then wall cloud region slightly weakens and then Y becomes wider, and finally I becomes open or the wall cloud region disrupts. The I or the region or the diameter of the eye or the area of the eye is closely associated with the intensity of the tropical cyclones. I is warmer than surrounding. I has a descending upper air which is cold. If the descent is adiabatic, but why is the I warmer than surroundings? As I told you, the cyclone is a warm core system, and you've got the maximum heating at 300 hectopascal or 10 kilometers. It is not a cold core system. Therefore, the area in the eye where the air is descending from the top towards the bottom is the warm air. Therefore, it is warmer compared to the surroundings. Yeah. Then usually tropical cyclones in northern hemisphere moves northwest direction. But why cyclone Nisarga moves northeast directions? Yeah. If you look at only the rotation of the Earth around its own axis, which leads to a force called as Coriolis force, because of that, the cyclone has to move northwestwards. But this is not the only force which determines the movement of the cyclones. As I told you, the cyclone is a kirk in the ocean. Just like a kirk in the ocean, a cyclone is just like a kirk in the atmosphere. Cyclone may be very large, having a size of 100 to 1000 kilometers, height of 10 to 15 kilometers. But if you consider the entire atmosphere, within that entire atmosphere, it is just like a kirk. So therefore, the motion of the cyclone or the movement of the cyclone is determined by the atmosphere in which it is embedded. If the atmosphere has a large scale wind distribution from east to west, then cyclone will move from east to west. So in case of Nisarga, if you just look at, there was an anticyclone located to the southeast of the system center. And cyclone Nisarga was lying in the periphery of that anticyclone. In the anticyclone, wind blows clockwise. So if you just imagine, anticyclone is there to the southeast of Nisarga, and wind therefore will be southerly to southwesterly. So therefore, initially it was moving northward and then became northeastward.
So as for the peripheral wind of the anticyclone, which was steering this cyclone Nisarga towards Maharashtra coast. Now, can you please explain which variables we can visualize to understand the rapid intensification process and the decay process of TCs? Rapid intensification is a very tricky process. Worldwide, it is a challenge. Um, the intensity as such, we have discussed, there are various parameters like sea surface temperature, ocean thermal energy, vertical wind shear, and relative vorticity in the lower tropospheric levels. And also, you have got supporting parameters like lower level convergence and upper level divergence in the atmosphere. In case of rapid intensification, what we have found from the study, that two are the important parameters. One is the sea surface temperature and associated ocean thermal energy. The other one is the vertical wind shear. If vertical wind shear is low and sea surface temperature is very high, as such the ocean thermal energy is quite high, it leads to rapid intensification. At the same time, if the cyclone is moving faster over the area where you have got this type of conditions, it will not show rapid intensification. Cyclone has to move slow over that area so that it is subjected to higher ocean thermal energy and lower vertical wind shear. It typically occurred in case of cyclone Amphan, which had got the highest intensity after 1999 Odisha super cyclone. That is super cyclone. It was in this year. And in that case, this Amphan was moving over the central Bay of Bengal, which was quite warm. Temperature was about 32 degrees Celsius, and ocean heat content was more than 120 kilojoule per cm square over that area. And it all supported because the cyclone was moving slowly over that area with a speed of about 4 to 5 kilometers per hour. At the same time, that area was also associated with very low vertical wind shear of 5 to 10 knots. So therefore, I will say rapid intensification is a tricky process. It depends upon mainly the ocean thermal energy or sea surface temperature and the lower vertical wind shear. But at the same time, other parameters like movement of the cyclones also determines the rapid intensification. I think, thank you very much for your very valuable questions and comments. I hope I tried my best to explain or to provide the reply to your questions. Thank you very much.
Thank you, sir. Thank you very much. We can go now offline.